morning, friends. You must be tired of seeing those expressions, and it is beneficial that we again ask ourselves, what are you doing? What are you doing? We are trying to develop a mathematical model which we will be using to characterize an airplane in terms of whether it is dynamically stable or not. As far as static stability is concerned, we have seen what are the conditions. But now we are doing a more generic way. We are trying to develop equations of motion and try to see that can I use this to comment on the dynamic stability of the airplane. And you know very well dynamic stability includes static stability for most cases, and for airplane it is very true. Then what was our approach? Our approach was we developed longitudinal perturbed equations of motion. And what exactly we mean by that? That we said, okay, this is my airplane. Let's say cruise is my equilibrium, right? And about cruise, I'll be giving a disturbance, small disturbance, and we'll try to see what happens. Please understand, the airplane is going like this. And now at cruise, if I am giving a disturbance, then we're talking about longitudinal case. That means it could have this motion, it could have this motion, it could have this motion. So there will be a perturbation in pitching motion. So we denoted that by small q. There will be perturbation in the speed. So there we denoted by small u. There will be perturbation in vertical velocity. We denoted that by small w. Okay. So u, q, small w, these are the perturbed quantities. And also we know that as this airplane is doing pitching like this and also doing plunging like this, there will be a change in alpha. We call rate of change of alpha becomes important, and we also note down that alpha dot also will play important role. Important role where? When I am trying to find out Fx, Fz and pitching moment, we said because of this small disturbance, this u will be there, the perturbed u, perturbed q pitch will be there, perturbed w component of the aircraft will be there, and also alpha dot will be there, because you can understand if a body is just moving like this, it is introducing an alpha dot, right? Because alpha is the angle between the velocity vector and the vertical component, right? So this alpha dot also will be there, and it is doing like this. As it is doing like this, there will be q as well as alpha dot, because what rate it is moving. So it is very obvious that we should include alpha dot. And then we said, okay, I write it as a function of q, then of course there is a delta E also, so it's alpha dot and delta E. Note down here we have written W, but here we have written alpha, because we know alpha is nothing but W by U1 approximately. So if there is a W, so there will be alpha. That is, if I take this body like this, and if there is an alpha here, perturbed alpha, then there will be a component of this velocity which is W along z direction, right? During perturbation, because we have used stability axis which is only at steady state. That direction is fixed under the condition of steady state. That is, at steady state, whatever the velocity vector is there, x-axis is there. But when there is a perturbation, then there will be a perturbed alpha. So we are talking about perturbed alpha. This is perturbed W, that is component along the z direction. Okay. Similarly here, you see, I could write u, q, alpha dot, delta E. In general, I will write here u, q, alpha dot, delta E. And one more thing we realized, please note that in the earlier lecture I have not put alpha dot. So we'll explain you, we'll do some approximations. But coming back to this, we understand that we want to ensure these arguments are non-dimensional, right? So we said, oh, instead of u, we'll write u by u1, Instead of Q, we will write QC by 2U1. Instead of alpha dot, we will write alpha dot C by 2U1. Because they are non-dimensional. Okay? All are non-dimensional, you see. Similarly here, again U by U1, QC by 2U1, then alpha dot, again alpha dot C by 2U1. Similar story here, this is QC by 2U1, alpha dot, again alpha dot C by 2U1. Because simply Q and alpha dot, they have dimension radians per second, right? Okay, fine. Once we agree to this, then we made an assumption that for normal airplane, small disturbance, I may eliminate alpha dot C by 2U1 effect on Fx for most of the airplane. So we wrote Fx equal to function of U by U1, then Q C by 2U1, comma alpha, comma delta E, right? Again further, for normal conventional airplane, you will see by experience, by results, this effect is also not that much. But have you understood what is this effect because of Q and what is this effect because of alpha dot? We will be discussing this today also, right? But at this point of time, we are assuming that this effect is also not that predominant. So Fx we wrote as F function of U by U1, alpha and delta E, right? And then we wrote this, expanded this by d Fxa by du by U1 into U by U1 plus d Fxa by d alpha into alpha, then d Fxa by d delta E into delta E, right? And this is Fx. What is Fx? Fx is the perturbed aerodynamic force. And then we know how to evaluate this. We are very clear. This has to be evaluated at steady state, and we have derived those expressions. And then we know explicitly what is the form of Fx, right? That we have done. Okay. I note down here this Q and alpha dot. We need attention. We need a discussion. We'll be doing before we go further. Similar thing we did for Fz. Okay. Here, although first lecture or maybe day before yesterday lecture, I have eliminated alpha dot C by 2U1, but let us keep it so that you also get some feel what is happening. Remember, alpha dot will have more effect on Fz in terms of lift rather than on drag. Although for all airplane, most of the airplane, we may still neglect this. But just to see that you are handy with handling alpha dot derivative, I'll be keeping it here. As far as moment is concerned, U by U1, Q, very important, because you know that CMQ will be very, very important derivative from dynamic stability point of view. Then alpha is there, alpha dot C also will be very important, and delta E. Okay, so we'll be developing expressions for all those derivatives. Now, till yesterday, when we used Fz, what we have done is, if I am not mistaken, we have written Fz equal to d Fza by du by U1 into U by U1 plus d Fza by d alpha into alpha plus d Fza by d Qc by 2U1 into Qc by 2U1 plus now we'll be adding d Fza by d alpha dot C by 2U1 into alpha dot C by 2U1 plus df Za by d delta E into delta E. So we are assuming that Fz will be function of U, Q, alpha and alpha dot and delta E, right? I might not have used alpha dot in the last lecture, but now we are relaxing, we are expanding, right? Because we are becoming comfortable in handling this. So if I want to know Fz, what I need to know? What is the expression for dFz by du by U1, which we have done. What is dFz A by d alpha? We have done. we will just check for this one and this one. This also we have already done in the last lecture. So today, first we will do dfza by dqc by 2u1 and dfza by d alpha dot 2u1. Okay? So let us focus on that. I have already mentioned about this dfza by dq c by 2u1, but let's see, I will revisit it again. Let us check the airplane. This is the airplane, okay, and this is the tail, and here is the wing, and let's say this is the CG of the airplane, right? What we are trying to find out? We are trying to find out what is that gradient or partial derivative dfza by dq, and of course qc by 2u means we are non-dimensional like this. The basic understanding is if I give a positive q, whether there will be change in the force in the z direction, okay, for a small perturbation. So now you see, if I give a perturbation q, small q, then what will happen? This man will go down. So there we know that here q into lt will be the relative air speed, right? Similarly, as this is the CG, so this portion goes down, so there will be also some sort of a relative air velocity. This portion also, all this portion also, ahead of CG. So you could see one thing. As it goes down, there is a force CL. Additional CL will come the vertical direction, which will be proportional to Q. And as it is going up, there will be some force coming down like this, right? But for an airplane, this portion is predominant as far as force is concerned between this and this, okay? So what do we do now? Because you understand another thing, that this LT is far larger, okay, compared to any center of pressure. If I take for the whatever the forces or pressure distribution gets generated because of Q, this length is smaller compared to this length, and this is not that lifting as compared to the tail. So tail will have more CL alpha, so that naturally that force will be more. And if I want to just check what is dCl by dQc by 2u1, and we just take tail contribution, because we are assuming that tail contribution is more significant. Some 10% you can add for fuselage, etc. contribution. Okay. So how do I find it out? So very simple. Because of Q, what is the delta alpha at tail? Additional, it is Q LT by U1 approximately. Right? So what is the force and the tail? L tail will be half rho V square at tail into S tail into CL alpha tail into alpha. Alpha is Q LT by U1. Okay. So then you are expert now. What is delta CL? Delta CL will be LT by half rho V square free stream into S reference. So this will become neta tail S tail by S reference into CL alpha tail into Q LT by U1. And what will be its sign? You could see that if it is going down like this, relative air is like this, so alpha into is positive, so delta CL will be in the lift direction. So as per the convention, that is a lift direction is opposite to the Z direction, right, for small alpha. So whatever you get here, right, remember, as far as CL is concerned, it is positive, but when you will be transforming it into Z direction, then it becomes negative. You will watch out for that, okay? So now this is delta CL. So we have delta CL is equal to neta ST by S reference into CL alpha tail into QLT by U1. And you know, DCL by DCL by D QC by 2U1 we have to find out. Since it is a linear, everything is linear, so I simply can write CLQ is equal to this divided by QC by 2U1, and that will be QC by 2u1. So u1, u1 will get cancelled, q gets cancelled. So I get dCl by dq, c by 2u1 is equal to 2 neta tail, s tail by s reference, which is wing, cl alpha tail, then lt by c. Okay? You could check here, q gets cancelled. So neta, then st by s, cl alpha tail, lt by this c bar, and 2 goes upward. So this is the expression for CLQ. Okay? So if this is the expression for CLQ, if I want to find how much delta CL is coming because of Q, what should be the answer? It is delta CLQ into QC by 2U1. That you should understand. It is not CLQ into Q, because CLQ we have defined as dCl by dQC by 2. That's important. Okay? So this is, you have understood what is CLQ. Now, we will not leave it here. We will also write, for completion, what we do, we'll, at one stage, we will also try to see what is CMQ. This will come. Okay? This is pitching moment, change in pitching moment because of Q. Okay, like it was change in CL because of Q. So this is also to be defined as dCm by dQc by 2U1. Okay? So let us derive this expression because we have come so close to force. Moment is very simple. So what will be CMQ? CMQ will be nothing but minus LT by C into CLQ, that is 2 neta S tail by S reference into CL alpha tail into LT by C. Right? This is CLQ. For example, if I want to find moment, this is the delta L into LT will be the moment. But we have to ensure that I should put minus sign. Why put minus sign? Because positive CL will give negative pitching moment, and sign conventions are from us. Right? So then you get an expression for CMQ as minus 2 neta ST by S into LT by C whole square, right, into CL alpha tail. And of course, there is a minus sign. This is, let me write correctly, minus 2 neta ST by S and LT by C whole square. So we know the expression of CMQ, we know the expression of CLQ. CMQ sign is why it is negative, that's very well known. If this is CG and if this is the tail, if I am giving a Q like this, so it is going down, so relative value is like this, the delta CL is here, and delta CL will give moment about CG nose down. So that is why this minus sign is here. Right? So we now know what is the expression CLQ and CMQ. Similarly, we will try to know the expression for CL alpha dot and CM alpha dot. Then again we will come back to the perturbed equation of motion. So we have understood CMQ and CLQ. This is done. Now we are focusing on CM alpha dot and CL alpha dot. And you know, CL alpha dot by definition we have said is dCl by d alpha dot C by 2U1, and CM alpha dot is dCm by d alpha dot C by 2U1. And you know why this C by 2U1? Because alpha dot has a dimension. We want to convert them into non-dimensional quantity. Now these are in textbook are covered under alpha dot derivative. Right? Let us understand one thing, very fundamental. If this is the wing, okay, and let's say this is the tail, wing and tail. As the airplane sees alpha, in this case the perturbed alpha, please understand this, it doesn't develop lift instantaneously. It takes some time to build the lift distribution. Understood this? So there is a time component. Although we assume if it is alpha, lift is CL alpha into alpha. But it takes time. It takes time to build that lift. So there is a time component here. Right? And second thing, so I write the build-up of lift on the wing, and textbook they also talk about indicial lift, right? Then second is very important. You remember because of finite wing, right? There will be vortices, right? Which will be traveling like this. They introduce downwash at the tail. They introduce downwash at the tail, so vortices or vortex, which is wing from wing, introduces downwash at tail, right? And what does this do? This downwash, say epsilon, it reduces alpha at the tail, right? So something alpha t minus or alpha 1 minus epsilon. So it gets reduced. Now you could see that if there is a time component in epsilon, right, that it is not that something fixed number, it is changing with time, then the angle of attack at the tail also becomes function of time, okay, even at steady state. But you have to be careful when I give this statement. What I am meaning is, please understand, these vortices will travel, right, approximately equal to the speed of the aircraft. There are debates, there are theories which says 50% speed, but I am assuming that it travels with the same speed of the airplane. So that means, suppose I am analyzing at time t, right? What is happening? At time t, the epsilon reduction will not be seen by the airplane because reduction in alpha will at tail will happen when? Will happen after some time, because these vortices will travel after some time to the tail. So then only the downwash angle will be seen by the tail at time t. That means what is happening? How much time it will take? Roughly it will take LT by U1. LT is the distance from the AC of the tail, AC of the wing to AC of the tail. I call it LT prime, let's say. Generally convention wise, LT is the distance between CG of the airplane and AC of the tail, but this is AC of the wing to AC of the tail, to be more precise. So what is happening? What is the understanding? If I am looking at time t, then the downwash seen by the tail will happen later at time LT by U1. That means for that time, the downwash is not seen by the wing, because if I start thinking at time t, the vortices are generated from the wing, so at that time t, this effect has not been felt by the tail, correct? That means when I am analyzing for time t, so this is actually seeing more angle, it is not seeing the epsilon. So that more angle will give me a downward movement, pitching moment, and that is Cm alpha dot, and the force is Cl alpha dot. Is it clear? Please understand again. I am focusing the phenomena at time t. At time t, I want to know what is the angle of attack at the wing, what is the angle of attack at the tail, correct? So at time t, the vortices will be generated, correct? But it will take around LT prime by U1 time to reach tail to give any downwash, correct? That means at time t, the downwash effect is not seen by the tail, so tail has more angle of attack, correct? Because tail will see the reduced angle of attack only after time LT by U1. So at time t, when I am analyzing, it is actually practically having more angle of attack than what we were thinking it should be minus epsilon. So that more angle of attack will give a pitching moment down or a force upward. So this will be associated to Cl alpha dot, and this moment will be associated to Cm alpha dot. This is the physics. Let's see how to develop the model. Okay? We will discuss this again in Man Ki Baat. I know there will be confusion, doesn't matter. we'll again discuss these things in Mann Ki Baat. So this Cm alpha dot is generally termed in textbook as lag in downwash effect. You understand what is this? Why this lag is there? Because at time t, when we are focusing at the wing, then it takes time Lt by u1 to reach to tail to have the downwash. So there is a lag. Downwash is at lag. Okay. So you know delta alpha will be how much? That will be d alpha by dt into delta t, and delta t is nothing but d alpha by dt into Lt by u1, right? And what is delta epsilon? Delta epsilon will be d epsilon by d alpha into delta alpha, and that is equal to d epsilon by d alpha into alpha dot into Lt by u1, right? So this delta epsilon, the angle of attack at the tail is more by this epsilon because it has not happened at time t. You have seen this delta epsilon is that angle which will be realized by the tail only after a time Lt by u1. That means at time t, this is the extra angle it has got. So I will write pitching moment or delta pitching moment as minus Cl alpha tail into this is d epsilon by d alpha into alpha dot into Lt by u1, that is Cl alpha into alpha, because this is the angle of attack more at the tail because the downwash has not reached or the vortices has not reached, so downwash is not effective, so angle of attack is more by this much. And this into, if you ask me, this into q tail, half rho v square tail into s tail into Lt will be the pitching moment, isn't it? Half rho v square tail, s tail, Cl alpha tail into alpha into moment arm is the pitching moment. No problem. Now you are expert. So delta Cm will be what? Delta Cm will be delta pitching moment divided by half rho v square s c bar. So delta Cm is delta pitching moment by half rho v square sc. In this case, v is nothing but u1 square. So now if I do that, what will happen? This qt and half rho u1 square. So delta Cm, if I write, this will be, this divided by this term, this will become nt. So minus sign is there, nt, and then s, st by s, and then c bar lt by c bar. This is there. And of course, we have Cl alpha tail d epsilon by d alpha into alpha dot Lt by u1. Right? Let us check. This is pitching moment divided by half rho u1 square sc. So half rho u1 square and q tail, this I represent by nt, this ratio, st by s taken care, Lt by c bar taken care, Lt by c bar taken care. Now what is happening? We are left with Cl alpha tail, which is here, d epsilon by d alpha here, alpha dot here, Lt by u1 here. Right? Now what is Cm alpha dot? So let us write here. So if delta Cm is equal to minus neta st by s, Lt by c, right? Cl alpha tail d epsilon by d alpha into alpha dot Lt by u1, then Cm alpha dot is nothing but delta Cm by alpha dot c by 2 u1, because we are taking all linear. So the slope. So if I divide it by what you call alpha dot c by 2 u1, what we will get? We will get Cm alpha dot equal to, see here, u1 and u1 will go. Then first of all 2 will come there, alpha dot will go, 2 neta st by s Lt by c whole square. You see, Lt by c here, LT is here, C is here, C bar is here. C means C bar, please understand that. And into CL alpha tail d epsilon by d alpha. Okay? So this is the expression for Cm alpha dot. So how to get the value for Cm alpha dot? You know, what you need is d epsilon by d alpha. And you know d epsilon by d alpha you can get for low speed by a simplified expression. And also there are empirical charts for that. Okay? So you have understood what is Cm alpha dot. So you can easily see what is Cl alpha dot if you just see how much is the force generated. Okay? That for that matter, I leave it to you and you try to find out the expression for Cl alpha dot. Okay? Clear? It's very simple here. You see delta epsilon is there, so you find lift equal to half rho v square at tail, S tail, Cl alpha tail into epsilon, delta epsilon. This expression is given by this, then follow the definition of Cl alpha dot and find it out. Okay? This I may give you in assignment also. I expect you to do these things.